Are you someone who always stubs their toes or hits their head on walls? Then look no further than quantum tunneling.
When my doctor recommended me quantum tunneling, it completely changed my life. All particles, like electrons and photons, have a property called wave-particle duality, where they behave as both a particle and a wave.
Waves are disturbances in space, but their exact position is unclear. On the other hand, particles have a clear position, but their wavelength is uncertain.
And according to Heisenberg's uncertainty principle, it's impossible to know both a particle's wavelength and position, because once you try to find for one variable, you lose information about the other. Luckily for us, quantum physics is probabilistic. So in a given space, a particle can exist here, 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 anywhere. Whoa, wait a minute. How can a particle exist in multiple places at once?
Pretend this ball is an electron. If I kicked it with a blindfold on, the ball could have made it in the goal, hit the crossbar, or missed entirely. Its position is uncertain. So unless I take my blindfold off and measure the result, the electron is said to exist in all three states, or a superposition of states. We can model the probability distribution of a particle's position with the wave function. The height of its peaks indicate the likelihood of a particle existing there, but not where it actually is. Particles have a low chance of being found here and a high chance of being found here.
Now let's say this ball is an electron that's traveling towards a barrier, let's say this hill. If it does not have enough kinetic energy to overcome the potential energy barrier, it will be reflected, or in this case, roll back. That's usually, not always. Since light is an electromagnetic wave, we can use it to model how the wave function would behave.
Light both reflects and refracts, but there's a
Specific angle in every medium where 100% of all the incoming light is reflected and not refracted. This is called total internal reflection. That's not true.
because according to Maxwell's equations, there's actually a small, rapidly decaying wave called an evanescent wave that forms at the boundary. Similar to light, if an electron's wave function hits a barrier, an evanescent wave is formed at the boundary. Now, if the barrier is thin enough, there's a chance that the evanescent wave doesn't completely decay and would actually continue traveling through the medium on the other side. Remember that the wave function represents the possible positions a particle can exist in. So if the wave exits on the other side, this means there's a small but non-zero chance that the electron can be here.
So does this mean I could finally live my superhero dream and run through walls?
Yes and no!
See, the greater a person's mass, the less chance they have of tunneling through. The chance is so unbelievably small, it's essentially zero. But essentially zero isn't zero. So for those of you who are always running into walls and stubbing their toes, just know that you may be lucky enough to escape another day of pain.